Hello everyone, and welcome to our presentation. Today we're going to talk about the consistent recovery threshold of hidden nearest neighbor graphs. And we're going to start from the Watts-Strogatz model of the small world networks, which is this simple network model that is used to model not only social networks, but also across a wide range of other disciplines such as medicine, biology, linguistics, and so on. And a small world network is generated as follows. So you start from a 2K nearest neighbor graph, which is a lattice network that looks like the one that is shown on the left. Given an ordering of n vertices, a 2K nearest neighbor graph is formed by connecting all the pairs of vertices that are of distance at most k from each other. So this way, each vertex would be connected to 2k of its neighbors. In the special case where k equals 1, this graph would simply be a Hamiltonian cycle. From this nearest neighbor graph, then each edge is selected with probability epsilon to be rewired to another node. An example of the rewired network is shown on the right. However, in real life, we never actually observe the underlying ordering of the vertices, and the observed network would look more like a graph like this. So our question is, from this observed graph, can we then go back and recover the hidden 2K nearest neighbor graph that we started with? This is an important question to ask because it is of practical value to distinguish strong ties from weak ties in networks. So for instance, in social networks, the strong ties represented by the edges in the hidden nearest neighbor graph could be looked at as links between close friends, and the weak links between acquaintances may be generated from the random rewiring process. We're actually going to look at the following more general 2K nearest neighbor graph model. So suppose we observe a weight matrix where we observe weights on all of the n choose 2 edges in the complete graph. We assume the edge weights are independent, and if an edge is in the hidden 2K nearest neighbor graph, we assume the weight is distributed as Pn, and otherwise it's distributed as Qn. If both P and Q are Bernoulli distributions with the following parameterization, then this hidden 2K nearest neighbor graph model would simplify to a variant of the aforementioned small world model with rewiring probability epsilon. Under this model, after we observe this weight matrix, the question that we study is, when is it possible for us to recover the hidden 2K nearest neighbor graph? And we're going to focus on two types of recoveries, exact and almost exact. Let's let x star be the adjacency vector of the true hidden 2K nearest neighbor graph, and let x hat be its estimator. We say that x hat achieves exact recovery if with high probability it recovers all the edges in x star. And we say x hat achieves almost exact recovery if it recovers almost all the edges. Now, to be more specific, since x star contains k times n edges, we say x hat achieves almost exact recovery if the expected Hamming distance between x hat and x star is of order little o of kn. This is our main result. Under mild assumptions on Pn and Qn, we show that for all k ranging from 2 to n to the little o1, exact recovery is possible if and only if the Rayleigh divergence of order a half between Pn and Qn reaches a certain threshold. And for all k ranging from 1 to little o of log n over log n, we showed that almost exact recovery is possible if and only if the KL divergence from Pn to Qn is above a certain threshold. Now, a couple comments on this result. Firstly, the special case of the small world model was studied in a previous paper by Cai, Liang, and Rocklin. However, the necessary and sufficient conditions given in that paper are suboptimal compared to our recovery thresholds. Also, in an earlier paper by my co-authors and their co-authors, they showed that in the case k equals 1, this is the sharp threshold for exact recovery. And if you compare this threshold with our results here, you'll see that from k equals 1 to k equals 2, there's this decrease in the difficulty in exact recovery. However, from that point on, the threshold for exact recovery just stays unchanged for a wide range of k. On the other hand, almost exact recovery gets easier and easier as k grows. It is not immediately obvious why that is the case. So next, I would like to go through some outlines of the key steps in the proof, which will hopefully provide some intuition on why the sharp recovery thresholds are the way that they are. We're going to focus on exact recovery, and we need to establish both the sufficiency and the necessity conditions. The necessity direction is easier to see, so let's start with that. Let's say the Xu graph X star corresponds to an underlying Xu ordering that is the identity ordering. Then if exact recovery is possible, then it must be possible to distinguish X star with any other alternative solution X. So let's consider the following sort of alternative solutions. From the identity ordering sigma star, let's just swap the rows of I and I plus 1. And after this swapping operation, you'll see that 4 mistakes in edge sets are created, and these 4 mistakes are represented by this difference graph here. So for an alternative solution X, its difference graph simply contains all the edges where X and X star are different. For example, if you look at the thick red edge from I minus k to I, it is an edge in X star because under the Xu ordering, the vertices I minus k and I, they're of distance k to each other. So they are k nearest neighbors, this edge shows up in X star. However, after the swapping operation, I minus k and I are suddenly now of distance k plus 1 to each other, so this edge does not show up in X. The other type of mistake is represented by the blue edges in the picture, which are edges that are not in X star but are in X. So under our model, if an edge is a red edge, then its edge weight is distributed as Pn, and the edge weights for the blue edges are distributed as Qn. So that is saying if exact recovery is possible, Pn and Qn must be far enough apart so that it is possible to tell the difference between these red edges and the blue edges. And that is how we were able to derive a necessary condition for exact recovery. I would like to point out that this example also illustrates why as k grows from k equals 2, there's no decrease in the difficulty of exact recovery. As you can see here, no matter how large k grows, this type of swapping operation is always going to create 4 edges in the difference graph. And as a result, the task of recovering the local graph structure sort of runs into this bottleneck. While on the other hand, if x hat is only required to achieve almost exact recovery, then it's only required to get almost all the edges correctly, and that is more of a global recovery guarantee. And as k grows, because there are more edges in x star, these additional edges provide more information that are helpful in inferring the global graph structure. And that is the reason why, as k grows, almost exact recovery just gets easier and easier. Next, let's move to the proof of the sufficiency direction. Suppose that we're above the recovery threshold. Then we need to show that the maximum likelihood estimator achieves exact recovery. Or in other words, we need to show that the likelihood at x star is not beaten by any other alternative solution x. And as before, we're going to associate x with its difference graph, which are these bicolored graphs. So if an edge is in x star but not in x, it's colored red, and otherwise it's colored blue. One observation is that because x and x star are both two k-nearest neighbor graphs, they contain the same number of edges. And therefore, the difference graph always contains the same number of red edges and blue edges. Moreover, the distribution of the log likelihood ratio between x and x star only depends on the number of red edges and blue edges in the difference graph. Therefore, via a simple union bound and the Chernoff inequality, we can derive the following upper bound on the maximum likelihood estimator's probability of error. So from this point, all that we need to do is to establish a tight upper bound on the number of alternative solutions whose difference graphs contain a certain number of red edges in the difference graph. So to that end, we're going to use the following combinatorial upper bound. However, the counting arguments that led to this upper bound are the most challenging part of our proof. And we're not going to have the time for the full proof here. However, I would like to just use a simple example to illustrate where this upper bound comes from. This example, by the way, also explains why when you go from k equals 1 to k equals 2, all of a sudden there's this decrease in the difficulty of exact recovery. So once again, let's say that x star is identified with the identity ordering. Then consider the alternative ordering that is shown on the figure to the left, which basically traverses a certain segment of the vertices in the reversed order. So the difference graph that corresponds to this alternative ordering when k equals 1 contains only 2 red edges and 2 blue edges. But we observed that as k grows from 1 to 2, then all of a sudden the difference graph contains a lot more edges. And those edges would provide stronger signal to help distinguish x star from this type of alternative solutions, making exact recovery easier. The key observation from this example is that when k is strictly larger than 1, it seems very hard to disturb an edge in the graph without also disturbing some other edge that is nearby. And that's actually the key piece of intuition that we relied on in the counting argument. So we showed that when k is strictly larger than 1, each red edge in the difference graph can help determine at least another red edge that is close by, which then allowed us to group up the red edges and then count them in a much more efficient manner. Next, I would like to use the remaining time to discuss some computationally efficient algorithms. Even though the maximum likelihood estimator achieves the sharp threshold for recovery, it is not computable in polynomial time. And it is still an open problem whether or not we can develop a computationally efficient algorithm that also achieves these sharp thresholds. We looked into a few algorithms, including, for example, a relaxation of the maximum likelihood estimator to computable integer linear program by dropping the constraint that x hat has to be a 2k nearest neighbor graph. We also looked into the linear program relaxation by further dropping the constraint that x hat only can only take integer values. We showed that both these relaxations achieve a recovery threshold that is only off by a factor of 2 compared to the sharp threshold. However, we also showed that this factor of 2 cannot be removed. Other than those, we also studied a thresholding estimator and looked into the spectral methods. All these methods, though, provably fail to attain the sharp threshold. Our positive result is that in the special case, that corresponds to the small world model, we were able to develop a polynomial time algorithm that attains the sharp threshold for exact recovery. However, this algorithm heavily relies on the fact that the edge weights are binary, and at the moment it is unclear to us whether or not this algorithm can be extended to our more general hidden Tucanius neighbor graph model. So that is everything that we wanted to talk about. Thank you very much for listening.